Today, I'm going to talk you through how to do equilibrium for bases. The key to determining the pH of basic solutions is to recognize that in an equilibrium sense, bases work exactly the same way acids do. Just as there are strong and weak acids, there are both strong and weak bases. So strong bases would completely dissociate. So we can look at this example here of lithium hydroxide that's on the screen. We can use this as our getting started with example. LiOH is a strong base. Now you could figure that out by looking up the Kb value. So the equilibrium concentration of the hydroxide part of the lithium hydroxide here would be equal to the initial concentration of the, here I'll just write, the initial LiOH concentration is going to be equal to the equilibrium concentration of the hydroxide. So in this case, we have mass and volume, so we have to calculate the concentration of the lithium hydroxide. So LiOH, the molarity or the concentration, remember, is moles per liter. So 4.63 grams of LiOH divided by its molar mass, 23.95 grams per mole. And then divide that by the 0.4 liters. Got to convert this to liters. And so you end up with 0.482 molar LiOH. Initially, you can put a little 0 here so that we know this is the initial concentration of the lithium hydroxide. And since the initial is equal to the equilibrium concentration of the OH, we know then that it's going to be 0.482 also. And then we just do the POH instead of the pH, so the negative log of the hydroxide concentration. And POH then, if you do that calculation, is 0.316. So there is the answer. And this should say POH, by the way. Oh, wait a minute. Nope. It should say pH. Now that we have POH, we have to do one more step. Remember, pH plus POH is equal to 14. So if we take 0.316 and set it up in that equation, since we know what POH is, we can easily find the pH. It's just taking the 14 and subtracting the 0.316. So you get, what is my number, 13.68. Answer to this problem. This is the other situation that you're going to encounter, and that is the pH of a weak base. When you have weak bases, then our equilibrium is going to shift to the other side. So instead of it being shifting completely to the far right, it's going to be more toward the far left. So the strategy is the same for weak bases as it was for weak acids. You're going to have to do some assumptions and the 5% testing, and then the use of the quadratic equation if it fails the assumption test. So here's the first one. Calculate the pH of a 0.35 molar solution of methylamine, CH3NH2. Notice we write Kb instead of Ka. That's another difference. And this particular Kb is 4.38 times 10 to the negative fourth. So we will proceed with the same strategy that we used with the weak acids. So the first thing we're going to want to do is write a balanced equation. So methylamine aqueous plus water gives us CH3NH3. That's where the hydrogens are going to add. And that will be, make it a positive. And then OH is what makes this a basic kind of situation here. So if I take the Kb value and I write an equilibrium expression for this, it's going to be products over reactants again. So water can supply the OH. The value of Kw is small relative to this Kb value of methylamine. So the OH negative due to water can be neglected. And it's the same as the weak acids when we neglected the water providing any of the hydrogen ions. So it's the same here for the Kb. So the next thing we're going to do is the ice chart, and I'm just going to build it under here following my balanced equation above. So initially we have 0.35 molar methylamine. Over here, we're going to have a negative change, which we will give as, I'm sorry, did I do that right? It should be a positive change, my bad. And this will be the negative. There we go. Okay, back up. Mrs. Keys had it. I really do need to put the balanced equation right above so I don't get mixed up. Okay, so initially these should be 0. And now we have plus x and plus x. There we go. Where did my paper go? There we go. Okay. Equilibrium then 0.35 minus x and x and x. And then we can plug in. We know that Kb value is 0.438, 4.38 times 10 to the negative fourth equals products x squared over reactants. We can go ahead and use the assumption rule. So we'll just take off the x in the bottom here. And we'll check it after we've calculated the x. So go ahead and you can calculate the x. You have your calculator with you. and that's going to be equal to both the OH and the CH3 and H3 plus. Hopefully, if you calculated this on your own, it was found to be 0.0124 molar. And then we can test our assumption. Oh, let me scroll my page here out of the bottom. We're going to test our assumption. So we have 0.0124 of 0.35. That should be around 3.5%. So we say it's okay. It's within the 5%. So now we can calculate the POH by taking the negative log of the calculated amount up here. When you do the negative log, you get 1.91. To find the pH, you're just going to take 14 minus 1.91, like we did earlier, and you get 12.09. I would highly recommend that you guys do these calculations with me, even though I'm showing you what the answers are, because on your homework, some of you were just making calculator errors. You had the right process, but you were coming up with different answers. So it's just a good practice to make sure that you're actually calculating correctly. Remember, you can also check your numbers, and that is by calculating the KB with the values that you've given yourself. So 0.0124 is both our OH and our CH3, so we can square that and then divide it by the concentration of the methylamine. And when we do that, hopefully we come up with a number close to our given KB, and this is what it came out to be. And so since these are equal, or very close to being equal, we know that our answer is correct. So there's other ways that you can check your answers. All right, are there any questions on these weak base problems? Okay, so this is going to be the assignment topic that you guys are going to work on this week is just working more equilibrium problems with the weak and strong bases. So let's flip in your book. I'm just looking for maybe an example that we can do in your book. Oh, let's just try 81. Well, no, that's too easy. That's pH. Okay, let's go to 83 instead. And let me switch apps here so that I can just write freely. Okay, so 81, no, 83, sorry, number 83. What are the major species in 0.15 molar solution of the following bases? So we'll start with A, so KOH. What are the major species? And then what is the OH negative? So the concentration of the hydroxide ion and the pH of the solution. So first of all, you probably would like to have a list of strong bases. So strong bases would include things like sodium hydroxide, potassium hydroxide. We did lithium hydroxide as an example. So notice these are all group 1 bases. Calcium hydroxide would also have be in the strong base category. So this is a strong base. So we know that there is 100% dissociation. We would say that, so it's far to the right. So the KOH concentration initially is going to be equivalent to the OH negative concentration at equilibrium. So does it give us, oh, it's 1.15. So 0.15 molar. So that's going to mean its concentration of OH is also 0.15 molar. So then we calculate the POH. POH equals the negative log of the hydroxide concentration. And I'll let you calculate that and you can respond to me. Unmute yourself and tell me the answer.
.824.
Right, 0.824. Okay, and if we're trying to find pH, we're going to go 14 minus 0.824. And that is equal to 13 13.176. Okay, so there's another strong base kind of problem for you. 87, let's flip over to 87. 87 gives us an example of a weak base. So what are the major species in a 0.15 molar NH3 solution? And basically we're doing the same thing, just with an NH3 is 0.150. That's the initial concentration. So if you look at 685 in your textbook, you will see some common weak base KB values. And on the list, we have NH3. The KB for NH3 is 1.8 times 10 to the negative fifth. So that means that this is a weak base. So we're going to write our balanced equation here. So NH3 aqueous. And since we're going to ignore water, I'm not going to write it in here. So NH4 aqueous plus OH minus is the balanced equation. We can do the ice chart. So initially I have 0.15 molar. We're going to have X and X. Nope, I did it again. I'm getting ahead of myself. Initially, we have nothing. This is going to be minus X and X and 0.150 minus X, X and X. So 1.8, which is the KB value, times 10 to the negative fifth is products, X squared over reactants, 0.150 minus X. You can use an assumption to simplify your math here, of course, but always check. So X squared over 0.150 equals the KB over here. So when you calculate this, this is going to be your hydroxide ion concentration that we're interested in. So go ahead and calculate that and unmute yourself and give me an answer. Benjamin, you got it?
No, not yet.
Okay. So you're on the hot seat. When you get it, tell us what it is.
0.0016.
There we go. So this is the concentration of the hydroxide. Notice that, well, we can test it, right, to see if it's appropriate. It comes out to be about 1.1%. So our assumption is okay. So we can then go on to calculating our POH, which is the negative log of 0.0016. And that comes out to be 2.8. Then to calculate pH, we just subtract that from 14, and we get 11.2.